My name is Sanjay Nagaraj, and I'm one of the co-organizers of this Biotech conference. We're excited to have you here, and hope you are equally excited as we are for today's exciting lineup of speakers and candidates. Get ready to hear from an unparalleled set of individuals in both industry and academia, all packed into a single day's lineup. We have a couple ground rules before we get started. First, please mute or silence all cell phones and remain seated during presentations. We have water and snacks outside for everyone to enjoy before lunch, but please make sure to remain outside until the presentation is finished and go outside to get water or snacks. The restroom will be to the right of the building and the whiteboard outside to show you how to get there. I will now turn it over to Edward, who's going to be introducing SSB, the club hosting this conference, before we get into this exciting day. Thank you.
Hello everyone, my name is Edward. I am one of the co-presidents for Stanford Student Biodesign, the organization hosting this conference and co-sponsoring and hosting this conference. SSB is Stanford's largest flagship biotech bioengineering organization on campus. We have over 120 members in our organization, hosting events, working on projects with different professors, bringing in speakers, running a medtech incubator course, and hosting our annual conference. We have done things by publishing on the Journal of Global Health, focused on creating a COVID-19 prophylaxis. We have many startups and projects that have been developed from our incubator course, which go into Stanford Biodesign and have become real startups. So this is a great opportunity for students to get involved and kind of explore bioengineering and biotechnology. This is our first year in person for conference since COVID-19, and we're so grateful that all of you guys were able to show up and that we were able to live stream this to the rest of the world. So thank you guys so much, and hope you guys enjoy.
All right, thank you, Edward, for the introduction of SSB. So now we're going to move into our first session, which is going to be about robotics and biology, a conversation with David Jaffe and Professor Monroe Kennedy. So before we bring up our first speaker, I'll just give a quick introduction of our first speaker, David Jaffe. And then from there, we'll turn it over to his presentation, followed by a quick introduction of Professor Kennedy, followed by a quick presentation by him, and lastly, finally, following up with a moderated Q&A session with audience questions at the end. So, David Jaffe received his bachelor's degree in electrical engineering from the University of Michigan in 1970 and his master's in biomedical engineering from Northwestern in 1973. He was a research biomedical engineer at the VA Palo Alto healthcare system, building, developing, testing, and bringing to market microcomputer-based devices for veterans with disabilities, including communication, mobility, and information systems. He's worked on several VA-assistive technology projects, including an innovative wheelchair interface for individuals with quadriplegia, an electromechanical finger-spelling hand that serves as a communication device for people who are deaf and blind, and a system that explores virtual reality techniques to train individuals with gait deficits to improve their walking, amongst many others. He also teaches a course at Stanford here, Engineering 110 or 210, Perspectives in Assistive Technology, and we'll be briefly speaking about that course today as well. So now please, I'm glad to introduce David Jaffe and get excited for his presentation.
About that. Good morning, everybody. I'm Dave Jaffe, and I'm going to be talking a little bit about assistive technology. Who knows something about assistive technology? Raise your hand. All right. A girl. Yeah, so I've been working here at Stanford, teaching my course for 17 years, and I'm going to be talking a little bit about the definition of assistive technology, and going to provide a few examples of student projects from my class from last year. Yeah, definitions. So, you know, the most common definition of assistive technology is a device-oriented definition, where we talk about try to read this, piece of equipment or product that is purchased or made from scratch to improve the functional capabilities of people living with disabilities or older adults. But that definition is pretty lacking from my point of view, and over time I've come to a broader definition, which includes not only devices but services and policies, institutions and facilities, and a design process. And the AT device is a product that we all think about, but a service provides various resources to people with disabilities, and AT policies and laws and legislation mandates the provision of these devices and services. And finally, engineers employ an assistive technology process to bring to market new devices. So assistive technology devices provide greater independence, increased opportunities for participation, and improved quality of life for people with disabilities by enabling them to perform tasks that were formerly unable to accomplish or had difficulty accomplishing or required assistance through advanced or alternate methods of interacting with the world around them. But you know, we all use devices that do exactly the same thing, that improve our lives, enable us to live the way we want to live, and enable us to accomplish things that we would have trouble doing without them. Assistive technology devices often employ novel designs and benefit and improve the lives of people with disabilities. And some of those assistive technologies are computers, robotics, mechatronics, nanotechnology, medical technologies, wearable devices, and lots of others. But, you know, we all use devices that do the same thing in the same categories. So that leads me to conclude that everything is assistive technology. You know, our cars, transportation. The institutions, all the networks that we use every day, electricity, computers, the internet, and so on. But the greatest piece of assistive technology is Stanford University, okay? Because, you know, this is an excellent place to learn about these things. And the zenith of assistive technology is me being here today telling you about assistive technology in this environment in Stanford. Okay. So there's a lot of people that work in assistive technology, not just engineers. You have physicians, therapists, suppliers, policymakers, educators, caregivers, and there are engineers that work in assistive technology too, to build devices, do research and development, technology transfer, marketing these devices, providing them in education and training. So this slide is actually pretty important. You know, there's lots of people with disabilities in the U.S. and around the world. I heard a figure this week of over 2 billion people worldwide with a disability. And in the United States, it's about 1 in 4 people that have a disability. But you might think, this is a great population of people to address their problems, but it's not a homogeneous group at all. Everybody is a little bit different. There are no 2 people who use wheelchairs that are exactly the same. I've never seen 2 wheelchair users with the same wheelchair set up in exactly the same way. So everybody has a unique personality and challenges and goals in their lives and aesthetic preferences. So that what happens there is that fragments the markets for assistive technology basically down to the individual. So assistive technology, pretty much has to be customized and personalized to make it work correctly. So this issue, because there isn't a well-defined mass market, means that companies that want to make products, and everybody wants to make products, a million of them exactly the same, that doesn't work. And this is a huge tension, and it results in products that are expensive and companies that are small. Okay, so if you'd like to hear more about assistive technology, please let me know, because I have a longer presentation that I can do as a webinar in the future. So please let me know, and that would include universal design and lots of examples of assistive technology. But to conclude, I'm going to just talk about 4 projects from my course from this last quarter, which I think are very illuminating. The course is a 10-week course here at Stanford. We had teams of 4 work on 9 projects, and their deliverables include not only their functioning device, but presentations and reports. The first one was this project, aesthetic prosthetic leg for Mary, who is a student here at Stanford. She would, and on the bottom you can see her, the challenge that she brought to the class. She would like to have the ability to dress up her leg through coverings to match her outfit. So the students came up with this device which fits over her leg and can be adapted to different colors and vinyl stickers and stuff like that. So that was pretty neat. She was very happy with that. This is the lower leg of Cat, and next to Cat is her dog. And she had a very interesting challenge. She has nerve damage in her shin, which results in it being painful for her to attend music concerts. The sound just hurt her. And she would really like to go because her friend likes to go, and this is a real issue for her. So the students came up with this sleeve that fits over her shin that blocks a lot of the sound and apparently works really well. So that's sort of a piece of assistive technology that you wouldn't have thought of doing. This device, a communication aid for Nathan, is an outgrowth of the movie Up, and the dog in the movie, you might recall, was named Doug, D-U-G. So every owner of a service animal has a problem. And the problem is that people see the service dog as a pet, something to be petted, to introduce yourself to, and that's very distracting for a dog that's in service of the owner. So, the service dog owners have to continually tell people, don't disrupt my dog. He's working, so the students came up with this device. It's on the left is a Bluetooth speaker, and on the right is a Bluetooth transmitter that actually transmits audio, one of 4 messages in this case, that gets sent to the speaker and spoken. So the speaker could be put on the dog, and maybe somebody could come up with a message as if the dog were talking, like in Doug. But unfortunately, in this particular case, the harness that the dog wears can't accommodate the speaker. So the speaker in this case would go on the wheelchair. Okay. The last project I want to talk about is this simple one. Everybody who uses a wheelchair needs a lap tray. And we've done about a dozen of these over the years in the course. And the one issue is that they're all different. Everybody requires something else. So wheelchair is different, so on. This particular one is interesting because it mounts between the cushion and the wheelchair underneath, and is supported by this vertical rod and a nice acrylic base that has room for her computer and her mouse. And it works out pretty good. It can be taken apart and be put in her backpack and to provide the mobility that she needs. So here's the website for my course, Perspectives in Assistive Technology. Please check it out, and if you want to contact me, that's my email address. I'll be around all day. I have some handouts and cards, so please get in touch with me if you're interested. Thank you very much.
All right, thank you so much. So now I'll be doing a quick introduction of Professor Monroe Kennedy, and then he'll be presenting on some of his research that he does here at Stanford. So Professor Monroe Kennedy is an assistant professor of mechanical engineering with the courtesy appointment in computer science. He received his PhD in mechanical engineering and applied mechanics and a master's in robotics from the University of Pennsylvania. At Stanford, he's director of the Assistive Robotics and Manipulation Lab, ARM Lab, whose broad research objective is to develop technology that improves everyday life, but anticipating and acting on the needs of human counterparts. The ARM Lab focuses heavily on both analytical and experimental components of collaborative robotics. Research applications include autonomous assistive technology, robotic assistance, and with the goal of deployment for service tasks that may be highly dynamic and require dexterity, situational awareness, and human-robotic collaborations. So, thank you so much.
All right, hello, thank you very much for that introduction. Let's see, does this one work? Okay, perfect. All right, yeah, so today I'm going to talk to you about collaborative robots and how they can really merge with this idea of wearable assistive technology. So as mentioned, I direct the Assistive Robotics and Manipulation Lab. Broadly speaking, we look at collaborative robots, which means how can robots actually be effective companions for people? And we start there and we ask many different questions in many different domains. Some of them involve thinking about like how do you actually physically design a robotic system? How do you make that system intelligent so that it can see the world, think about the world, then act on what it knows? And then how can this robot be an effective teammate for other robots or potentially people? Across this domain, we saw problems saying, well, if we want these types of robots in human spaces, they need to be effective at manipulating things like humans do. They need to be able to perceive the environment and draw conclusions. So if they watch a ball move, can they infer its dynamics, for instance? Can they learn how to do things effectively by watching people do them? And if they watch people even collaborate and do team-like activities, can they then substitute in and be a good teammate like people? If we actually physically attach them to people, can they actually infer what the person wants to do, adapt to them, and allow them to complete a complex task, perhaps a manipulation task? If we place these devices on a person, can they actually do assistive roles such as alerting them if there's something in the environment that might cause them to fall, understanding, therefore, how the person is moving, the environment, and how the person might be making decisions as they move through that environment? in the next few minutes here, I'm going to briefly touch on these three domain areas. But to kind of set the tone here, let's think about someone reaching to grab a cup. Very easy for you or me. But if we kind of look at a spectrum of different types of disabilities, you might have cases where the person has full actuation, where they can actually reach towards something, but maybe their muscles are firing in a way that's undesired. And then on the other end of the spectrum, perhaps it's underactuated. They don't have the ability to reach fully toward an item. Either their arm may not work, or even they may be missing part or all of their arm. So if we look at this sort of spectrum of disability in this way, you have this sort of unintentional involuntary muscle contractions. I highlight some work here by Peter Tass here at Stanford, which has a very cool glove you can wear that can actually help to dissipate and calm down these signals for unwanted overactuation, if you will, of a muscle. Then if the person is has lost their arm, the question is, to do the task, could they control maybe a passive wearable device to kind of do what they want? And so here you can see this individual, he's able to manipulate the screwdriver and do a set of household tasks here with this sort of passive hook device. But that's great if your kind of manipulation tasks matches to the amount of actuation you can provide. He's controlling this through how he actuates the rest of his body, often in a sort of cable-driven type of system. But if I want to do a more fine-tuned manipulation task, maybe with your hands, take any one of the tasks you see here, opening a bag, opening a container, all of these, I need more dexterity, perhaps, than what a hook could provide. And I can always pick a task for you, tying your shoes or whatever, that just becomes more challenging. And even if it's possible via a sort of tool like a hook, the question could also be, how long would it take you to complete it? And is that frustrating? How is your quality of life for the complexity of the task that you're being asked to complete? And something I want to draw your attention to, and hopefully you can see it here, is this arm is being essentially on the far right here, being used to brace against an object, and it's not really doing the dexterity task. The other hand, the able-bodied part of the hand, is actually the one completing the most complex part of this task. To really drive this home, I have this quick video I pulled off of YouTube. Here, this individual has damaged their right hand, and to open this pill container, to successfully do this, which is an everyday task, I'm sure we all have taken medication with these types of caps before, this required a special rubber base to provide an alternate force to brace. You had to push down and then kind of twist. And you know, if you think about even the number of trials, this is only 10 seconds of a very much longer video. This was a very complex thing for even an able-bodied person to complete. And yes, you know, this individual has had a chance to practice this, but this is still very hard. And so there's also this aspect of a learning curve. If you just got a disability, how long would it take you to actually be good at doing these types of things? So what my lab comes to is we say, well, it's really hard, specifically as these tasks become more complicated. How can we actually provide a system that can really just, as an observer, understand what you're trying to do, understand where you are in that process, and apply a degree of intelligence and physical capability to help you accomplish that goal? So this enters the space of collaborative robotics. I give this slide always just to really paint a picture of how far we've come. I'm not sure if every video on here is playing. Yeah, I should have made some of these GIFs. I really encourage you to go check out some of these really cool videos with Boston Dynamics. You have these parkour running robots doing all these amazing things. We can do a lot with computer vision and even kind of general motion of manipulators. But whenever we want to do that kind of dexterous task, like opening that canister, this is still really hard. And it's because robots don't have the same sense of touch as us. If I think about all the things you could potentially feel in the sense of touch, there are a lot of forces you could feel at the surface: the normal force, the planar force, shear force, and rotation. These are all the components. And this is a mathematical slide from mechanical engineering, continuum mechanics. I blow up just a fraction of a material and say, what are all the forces that could be acting on the surface? This gives you a description. So if you had a good force sensor, these are the things that you could sense: the normal force, shear force, and torsion. Looking at how biology solves this, we have mechanoreceptors inside of our fingertips. They're kind of like cell pouches. There's 4 different types. Based on how you actuate, you can sense different types of things like forces or shape. And these are sent to your cortex and used to actually interpret the shape and forces at the point of contact. A really interesting study showed that the part of your brain that actually does the sort of sensing that you see here, if there was an experiment where if you held the person's hand in front of them and you had an intermediate layer that actually showed them an image of what their hand was, you could trick them. So in some cases, they're actually seeing something touching and the part of the brain that responds to that fired. And in other instances, you didn't actually touch them, but you showed them being touched. And that same part of the brain had a much smaller reaction, the part that was dedicated to actual feeling. And so we've already evolved, if you will, to actually understand the importance of the sense of vision in the role of understanding touch. And that drives me to the point in how we actually think about kind of sensing and finger sensing in our lab. One on the side of physical transduction, which is similar to your mechanoreceptors. You're mechanically bending something and that is sending an electrical signal. The other is optical based. If I put a camera inside of your finger, can I observe the point of contact and use that to tell me about the shape and stresses? And so this video that you see here, again, I encourage you to check out this YouTube video for a much higher resolution. We showed that we could actually use neural networks to observe the inside of a gel finger, the boundary, and can reconstruct the shape. And this is a regression problem, so you touch it, we can build a point cloud with an accuracy of within 280 microns for the sensor per pixel for this image. And then to kind of quickly show the real-time operation of this, again, you can see these videos also on our website. When we push, we can sense forces as well as the shape. And the way this is achieved is you kind of see this sort of dark pattern in the finger. It's kind of like a fingerprint. We can track the fingerprint deformation, and that tells us forces. And we have LEDs inside that shine color. And when you kind of tilt the surface at different angles, it changes the intensity because it correlates to the normal of that surface. And you can use that to integrate with Poisson integration to tell you the shape. And so I have quick videos here showing both the forces and the ability to sense shape as well in real time. And with this, you can do a lot of tasks that used to be fairly complex. So imagine picking up screws from a bin. You could actually accomplish things like that. And to kind of tie things together, imagine endowing, for instance, a prosthesis with this type of fingertip. What kind of capabilities could we give people with manipulators that can do things like this? I think this video isn't working, and that's fine. Yeah, anyway, we have an example where we actually show the ability to touch a pill, read a pill, and see its shape towards perhaps understanding what you're picking up when you want to place this in a person's hand. And we're shrinking this down, so this summer we'll have the 3rd version of our sensor, which will be the size of the human thumb. So moving to the other side of our work, which is how do robots then become good collaborators for humans, there's this notion of theory of the mind. To be a good teammate, I should anticipate you. And so that means I need to understand what you see, what you observe, and how you might make decisions so that I can anticipate you well and be a good teammate. So taking an example of 2 agents carrying an object from one side of an obstacle to another, you can think of this in sort of like a control sort of paradigm, where here we have the ability to model how a robot and a human makes decisions, that's their policy, how this affects the world, the dynamics in the plant, and then how you observe what happened and make decisions based on that. The best you can do is having a single mind that controls every single agent. It makes all the decisions, it sees everything, and it tells everyone what to do. But in reality, these are decentralized. They're not always communicating every aspect of information. Just some information is usually communicated. So thinking about how does the robot conceptualize the other agents in the teammate scenario, we can actually think of this sort of control paradigm as you see here. The robot and the human make some actions, affects the physical world. They both perceive, they have a mutual objective that they're trying to reach. And if the robot can conceptualize itself, the human, and the task and everything, it can even plan out ahead how the next few things should evolve in order to be effective. But the challenge here is inside of that robot's thinking, it actually has to have a confined model of how the human is thinking. And modeling how humans think generally is extremely hard, but maybe if we can say, well, we know you're trying to do this task, we can think about how you would approach this particular task, which brings us to the human's cognition. And specifically this notion of generative modeling. So if you were to do the same thing, drive down a lane, you might vary slightly in a lane that you're kind of staying in. You can use that knowledge about the variance to say, well, the human's actually gonna have some statistics in how they make their decisions based on what they see. And there might not only be a single modality in terms of a distribution, it might be multimodal, right? So how do they make these decisions? What is the distribution of decisions that they might make? How can I watch humans make these decisions and then build a distribution that matches that expected distribution that I observed in data? And so I list a few neural network architectures here. Machine learning can be very helpful for thinking of these statistical problems to accomplish this. Some of the more popular and recent ones are these flow-based models or diffusion models. So quickly showing some applications here. I mentioned the intelligent prosthetic arm. We have two tasks that we're working on now in the lab, sort of pick and place and a pouring task. And there's two paradigms, one in which you know how to complete the task, and the question is, of the tasks that can be done, what does the human want to do at this moment? How can you infer that perhaps from their gaze and electromyography input? The other side is, how would you actually teach the robot how to do something brand new? I give you a double amputee person. They want to teach the robot how to pick up and place something that has never been picked up and placed before. They need to be able to do this out in the wild. How would you accomplish that? And brain-computer interfaces and augmented reality can be a terrific tool for that, because I can actually have you demonstrate that virtually. So if I say, oh, I can use my computer vision to segment the world, I can say, well, this is a cylindrical object. I don't know what it is or how much it weighs or anything, but if I give you the ability to control a virtual cursor, could you show me how you'd want to do that interaction? And I'll ask you to do it a few times, not too many times, but after doing that virtually, can I then make your real arm go and do that the first time, allowing you to teach me in AR? Oh, wow, that's unfortunate. These videos, too, are really cool. What you see here is actually the augmented reality version of this arm. And so what we're able to actually do here is perform this pick and place task. And we're actually able to observe virtually what we want to pick up, and the arm is able to move and perform that pickup task. And so we're showing here the ability for our method to actually infer context of the task to improve the rate at which we perform it. The very last problem I'll mention is this fall prevention sensor. You're walking through an environment, you have a camera that you wear on your torso, it observes the scene, understands where you've gone, predicts where you're going to go, and is able to understand the risk of you falling over that expected path. We have a camera you wear on your torso, sensors on your legs, and we need some compute that you're carrying along the way to accomplish this. If I phrase this mathematically, I'm saying, given the past place that you've walked in the environment, can I predict where you're going to walk, the future, and how the environment will move around you as you walk forward? To accomplish that, we look at the surroundings, and kind of like the panorama images you have on your phone, we create a depth image panorama, and we feed that to a network as a consistent state dimension. To understand the risk of falling, we have this notion of a sway covariance metric, which says as a person walks, they'll have a particular cadence for their torso. If you excite them and pull them really hard, that'll actually increase dramatically. And so we can actually use that information to understand if they may be at risk of falling by watching that change in their cadence over time. And here's a fancy neural network that is able to take in the past and do that prediction for the future using a combination of autoencoders and recurrent neural networks, particularly in LSTM, to allow us to predict where you're going to go in the world and how the world will evolve around you. And we're able to show that we're able to do this quite well. We walk indoor and outdoors around campus. We're able to predict up to about 7 to 8 seconds in the future. And we show that if we actually are able to also visualize the world and not just predict from the past state, we can actually do an even better job of predicting where you're going to go. We have a really cool video on our website I would encourage you to go check out that shows the ability to observe the surroundings, the barriers, and predict how you would navigate them without collision. And we also show that we're able to predict how you would sway, and that's fantastic for ultimately being able to alert the person saying, we think that the feature in the environment, the curb, might make you trip. Therefore, here's an alert, slow down, and maybe we can interface with the lower limb exoskeleton. So what's next? We want to be able to say, well, we see an environment, can we predict all the possible paths you could walk through? Can we put all of this on a phone? And then can we deploy this to the communities that need them the most, like the elderly and possibly visually impaired or other neurological disorders? With that, I would like to say thank you.
So now we're moving towards a quick moderated Q&A with Professor Kennedy and David Jaffe, and then followed by a couple audience questions, and then that'll be at the end of this session. We'll have a quick 2-minute break and then move to our next session. All right. So the first question I have is directed towards you, David. So what do you think the future of assistive technology looks like? And are there any barriers that may be slowing down the impact of assistive technology to the general public?
Thanks for asking that question. Right. So in the future, I see advances in assistive technology and devices and thinking about these things and incorporation of the ongoing research into practical products. But these devices must be shown to be effective, or people won't use them. They need to be reimbursable by insurance so that people can buy them. They need to be affordable. Some of these prosthetics and exoskeleton products, are over $100,000, so that's really an issue. And finally, they must be known solutions, so people who prescribe them and doctors and therapists and other people must know about them and know that they would have an enhanced benefit for their clients. So,
yeah. Okay, thank you for that. So my next question is towards Professor Kennedy. So what do you think the future of bio-inspired robotics research looks like, and what types of robotic systems do you think will see widespread adoption in clinics and hospitals?
That's a great question. I think an interesting thing that you'll kind of notice if you look at the field of robotics is a lot of really cool work comes out of biomimetics. So you could take work from like Professor Mark Kukulski here at Stanford, and many others that really draw inspiration from how humans work in order to think about how we can make our systems more evolved. One of my favorite, I think, examples of this, like biology informing the science, is actually event-based cameras. So the way the human eye works, right? We actually have like cones inside of our eyes, and the way they don't fire like a traditional camera, like a rolling shutter and all at once. Each one of those cones spike and have their own particular event. Event-based cameras do like a log difference of the intensity of the pixels, and because of the way that they calculate things different than normal cameras, they're more robust to washout. So, one concern you might have is if you're driving a self-driving car, you ride up in the morning and just like you bring your visor down so that the sun doesn't blind you, this could totally blind your camera. And if you're in this kind of car, how do you handle that kind of scenario? Because you don't want to have washout, but you also want to make sure you see the thing in the road. There's this kind of duality here, which is a challenge. But event-based cameras, informed by the human eye, are actually able to accomplish this really well and don't suffer the effects of washout. The sun has its own intensity and it doesn't change, and so it disappears in this event-based image. But a person walking across the road, their pixel intensities would change and you would see them. So by combining an event-based camera with a regular camera, you now have this robustness and this technology that was directly informed by biology. So I think there are many times when we can actually look to biology as a great inspiration for how we might think about this. And in particular, something that my lab is interested in is, similar, I kind of mentioned what humans can do in the sense of touch. We're informed also by how that works. But also, if we want to have hands that have good strength-to-weight ratios like us, we might need to actually rethink what synthetic muscles might look like, and how can thinking about anthropomorphic design and informed kind of muscles like that, how could that improve the space of robotic manipulation? And then you mentioned like adoption to the clinical kind of space. I think, as we develop systems that are reliable and I think can augment the medical community, both for the patient as well as the doctor, effectively anticipating their needs, being able to do things functionally, I think we will see that adoption that comes along with utility and reliability.
And sort of just like quickly touching on sort of AI autonomy, what do you think that AI autonomy will really impact, or where will it have the most impact in terms of applications of things like personalized medicine?
Last part?
In terms of things like applications to personalized medicine.
Yeah. I think that's a really great question. And to that personalized aspect, which I think Dave also kind of brought up before, there is this need for adaptation to every particular user. But also, as Dave mentioned, if you try to have one size fits all and you're very rigid, then you're gonna not do anything well for anybody. So I think this just needs to become a part of the engineering problem, right? We have, seatbelts that work for many different people. Why? Because they adapt, right? So how can we think about our solutions that can adapt to a particular person's needs? Particularly thinking about the space of AI, one area that I'm really excited about is how we can even improve brain-computer interfaces with that kind of technology, right? So, even today, when someone trains to use a brain-computer interface like an EEG thing better, you have to have this whole period of calibration, right? And you're trying to interpret for them, given their particular, neurological setup, how can you adapt and understand their particular signals? So you can imagine having the ability to sense, first of all, and understand what inputs they can provide, but then having a model that can take those inputs, know what you're trying to reach, and adapt to their particular needs. So I think AI that is adaptable understands, the distribution of the problem and the prior, which can come from the engineer, but also has that inherent ability to adapt to the particular user, I think is an important direction forward, and something that machine learning, AI, and autonomy is well suited to solve.
Yeah, and the last question I have for both of you is, on a broader note, what is the best piece of advice you've ever received?
Okay, I was thinking about this because you gave me the questions beforehand. And so the best piece of advice was from my father, who told me, Dave, I heard that University of Michigan is a good school to go to, and so I did that, and it worked out really fine for me. But most of the things that I learned from are things that I perceive, rather than people telling me, do it this way, or I suggest you do it this way. I sort of, by observation and doing it, can see what's working and what isn't working, and this certainly applies to the course I teach. And so, every year, it's just another iteration, and with each iteration, I see, maybe I could have done it differently and it would be better, and I try that the next year, and that works out. So I've had 17 iterations on my class, and I think it's pretty close to being optimized. Well, I think so. Maybe some of the students don't think so.
Okay, so basically the best advice is just kind of doing and learning from what you're doing.
That's right.
Okay, and then Professor Kennedy?
I think that's a great question. I think if I try to narrow it down, I have received a lot of really good advice. I think I would pick one that kind of applies to problem solving, and it's to start with the big problems first. There's like the really fun story that you kind of hear that goes along with this, like the teacher is trying to teach the students how to pack the rocks into the container, and they put all those small rocks in first, and then the big rocks were kind of left out. But the moral of the story, you put the big rocks in first, and then the small rocks in on the side, and you're actually able to do a better fitting of this. And if you take that analogy and apply it to real life, we do this in research all the time. I have my students go through a critical analysis of the problems that they're trying to solve. Where do you perceive is the biggest challenge you're going to face as you go along in this problem? And if you have the natural human inclination to procrastinate that and go, we'll figure that out later, let's do the fun thing first, then you'll reach that problem, and it might be an impasse that might have slowed your entire progress down. So by thinking about the hardest piece and addressing that head on, I find can make a lot of things move a lot smoother. And I apply that as much as I can to our personal life. And it's an uphill battle because it's never fun to deal with the hardest and the non-fun things first. But if you do, generally, your life can be a lot smoother in the long run.
For sure. All right, now turning it over to the audience. Does anyone have any questions for either Professor Kennedy or for David Jaffe?
I have a question for Professor Kennedy. You mentioned human cognition modeling, right? And you enlisted what autoencoders, flow models, diffusion models. Again, you didn't mention transformers, right? You didn't mention emerging properties of very large language models like GPT-4 by OpenAI or PaLM by Google. Do you have anything to say about that?
So short answer, yes, they're important. I think in the last work that I showed you with the path prediction, we did have a recurrent model, which was like an LSTM type. You know, it's the dumber version, if you will, of like attention networks or transformers. Those can be very helpful. And to your point, right, for cognition modeling, any type of model that can leverage that sort of sequence knowledge is going to be extremely helpful. So the work that we're actually doing in my lab now, we're trying to better interpret input from like EMG sensors. We're using GRUs, which are sequence-based models, to help us understand that kind of phrasing for that signal processing. And we think that those will play a really big role when we do move to brain-computer interface interpreting, which we're trying to do in the near future. I think the reason I mentioned those particularly is because, right, that does have a very wide distribution. And if you also kind of lean in on the ChatGPT kind of conversation, it's not just the ability to do the sequence, it's also the fact that it's generative. And if I had to choose between those 2 points, I mean, they're both important, being able to understand how to predict a sequence from a sequence. But the other aspect is, well, how do you think about generation? And if I really think about human decision-making, I think generative modeling is slightly maybe even more important than the notion of even that long-term sequential modeling, just because some problems you can actually fit into a Markov decision process framework where maybe the past is not necessary for you to predict the future. You walk into this room right now, right, and perhaps only what you observe right now is what's going to drive your future decision making. In that instance, right, you know, I then need to understand the distribution over the types of decisions you might make. And so generative modeling and some of the methods that I showed are some of the leading approaches you might do for that. But to your point, there are many times, often, where that sequential knowledge can be very informative to condition on, and by all means, we take full advantage of that.
Yeah, we probably can take one more question. There's probably more time after during the networking lunch to ask more questions if you have any, but we can take one more right now in this session. Yeah.
So one of the things that AI is supposed to be very good at is hyper-personalization, right? And it can do it at almost zero marginal cost. You can get a different news feed from someone else and it doesn't cost the company anything different. And AI, as you mentioned, is also very good at enhancing the quality of some of these tools for the disabled people. So do you think in the next 5 years, we're going to see AI reducing costs of some of these assistive devices, or do you think it's going to be primarily used for improving the quality of some of these robotic assistants, and they will continue to remain costly? I just wanted a sort of a crystal ball on that.
Right. I think AI can be a great tool for assistive technology, and as Professor Kennedy mentioned, in the area of brain-computer interfaces, I can see that being used to enhance communication from a person who can't speak and can't move. But I can also see AI being used in optimizing algorithms for prosthetic devices and exoskeleton devices as well. And a lot of the work that Professor Steve Collins is doing, goes in that direction as well. And another application that I thought of is, there's so many assistive technology products out there, and knowledge of them, of all of them, is how can one person know not only of all the devices out there, but how they've worked when people have used them. So I can see AI as being sort of an advisor where you can input the characteristics of a person with a disability, and it could offer suggestions of products based upon what is on the market and how they perform with other people. I think that could be very helpful because all the time I see people asking questions. Basically, I have a client who is this and this and this, and I'm wondering what products, will work best for them. And it's good if you have a community of people who can respond to that, but it'd also be good to have a AI version of that to work on as well.
I think the really small thing I'd add is just what goes on underneath the hood, even for the ads. Like there's usually some sort of prior that you're conditioning on. And even when you shift it, right, like if I take a very large language model and I'm applying it to a new scenario, the transfer learning isn't changing every weight. It's kind of changing the last layer and doing a slight distribution shift. So you don't get away from the need of like having this underlying prior to be very helpful. But the question is, how good are you at taking that prior and performing that distribution shift to the new scenario? And the question is, how much work does that take? And was that first prior a good prior for whoever needs to use it next? So I think those are like some of the underlying problems for adaptability. And then I think from the mechanism side, it's really the Wild West. It's really hard to predict, what will be the next hot thing. My lab is pushing fingertips and hands, right? But without that kind of thing, those things might not exist. So, I think we're in a very exciting time. Every year and every 2 years, we see an amazing turnover and incredible technology. So I'm hopeful.
All right, please join me in giving them a round of applause. And like I mentioned, they'll be here. I think Professor Kennedy and both of them actually will be around at the lunch, so you can feel free to talk more with them about anything you want. So we'll have a quick 2-minute break now before moving into our next session. So feel free to get water or snacks outside and then make your way back to your seats. All right, we're now going to start the second session. So I'm going to be quickly introducing Professor Mark Schuyler Scott, an assistant professor in bioengineering here at Stanford, who focuses on developing new 3D printing technologies with particular applications in pediatric cardiology. So his lab focuses, like I mentioned, on pediatric cardiology and 3D bioprinting, and is embedded at the intersection of synthetic biology, tissue engineering, and 3D printing. And today's session will be discussing about 3D bioprinting and moving beyond the petri dish towards whole organ biofabrication. Thank you so much.
Great. Thank you to the organizers for inviting me to your session this morning. I will say I've come dressed as an assistant professor with 2 young children on a Saturday morning. So this is an optimized look, speaking about life advice, optimizing the minutes and the hours take care of themselves. So slip-on shoes, t-shirt, excellent when you need to be up at 5:15 a.m. But I'm actually really excited to talk with you and share some of our research in organ biofabrication. And I think it's great to come after a session talking about assistive technologies for people with impaired or absent limbs. And that's kind of the mechanical, mechatronic comparison of what we're trying to do, which is working with the squishy, the biology. So I want to start just with a conflict of interest statement. So our research focuses on children that are born with this condition called single ventricle disease. Most of you in this room have 4 chambers of the heart, 2 ventricles, 2 atria. Your right ventricle is designed to pump blood around your lungs to oxygenate the blood, and your left ventricle sends that oxygenated blood around the body to deliver the necessary oxygen and nutrients for your organs and limbs to survive. But a subset of patients are born with what is called a hypoplastic left ventricle. Their left ventricle fails to form. And instead, they only have one single, very large ventricle to which both the deoxygenated blood from the body and the oxygenated blood from the lungs enters. And as a result, this blood mixes, and you have semi-oxygenated purple blood being passed around the body instead of fully oxygenated blood from the lungs. Now, this used to be a deadly condition, and infants would survive only 2 weeks. But thanks to advances over the past 5 decades in surgeries, these patients undergo a pretty radical series of surgeries to result in what's called the Fontan circulation. This is where the deoxygenated blood from the body is connected directly to the pulmonary artery so that the blood only passes through the heart once per entire circulation of the body. And that blood is now expected to be ejected from the heart, travel around the body, come straight up to go back through the lungs before returning to the heart. Remarkably, this solves the mixing problem. Now all the blood returning to the heart is fully oxygenated, and the body is receiving fully oxygen-saturated blood. But the downside is this circulation results in very high back pressures, because the blood here that would expect to receive an extra energy kick from the heart before going to the lungs is now expected to travel through the pulmonary artery to a second capillary bed in the lungs before receiving that energy. And as a result, these patients typically only survive 2 to 3 decades on this circulation before they either need a heart transplant or they succumb to their disease. We want to do better. 2 to 3 decades of survival from a surgery is amazing if you're an adult, but these are children between 0 and 2 years old. It's not long enough. So what we want to do is replace this passive tube that gets put in to connect the inferior vena cava to the pulmonary artery and replace it with something that's living and beating and able to supply energy to the blood. That would be something that would need to look like this, 4.4 millimeter thick wall. It would need to be 3 inches long. It would need to have 3 billion cells in the conduit. All of those cells will need to have vasculature within that beating tissue to keep those cells happy and living. And there'll need to be a pair of valves to be able to achieve unidirectional flow. So unlike a lot of tissue engineering strategies that are working with small pieces of tissue in a petri dish, we really need to manufacture something near fist size to be able to have a physiologic impact on these patients. So our lab is focused on building a pipeline that goes from stem cells through building clusters of functional cells to introducing vasculature into the cells to maintain their viability and culturing them in large bioreactors to be able to gain enough cells to work at the physiologic scale. So thinking about the first challenge is how do we make enough complex pieces of tissue to be able to manufacture living tissue at large scale? And here we rely on the natural self-assembly capability of stem cells to deal with the hardest part of building the smallest structures. And there's a process called organoid development where you can coax stem cells in 3D to differentiate into organ-like tissues at the small scale. And many different versions of these organoids exist, be them kidney organoids or cerebral organoids or skin organoids. And a real challenge in this field is traditionally when you're trying to tell a stem cell to become a specific cell type, say a neuron specifically, you provide very specific instructions in the media that those cells are cultured in, so you get a high efficiency production of a single cell type. But our organs are not consisting of single cells. They have many different cells in the body, in each tissue. And if we want to be able to achieve greater complexity, we have to stop pushing the cells as specifically to become one cell type. And to do that, we nudge them, we guide them very delicately. So instead of giving specific instructions to become one cell, we give them instructions to become many different cell types. But as a result, it gets harder and harder to control exactly what they become because we start giving them much more unspecific cues. And this has been recognized in the field of organoid development that it's very difficult to overcome the reproducibility issue, getting the consistent tissue structure every time while trying to achieve many different cell types to be co-developing. So working with a pair of graduate students, Eric Liu and Jeremy Huang, we devised a method to, instead of externally telling every cell what to become, what if we genetically engineered different populations of cells such that each one is specifically instructed which cell type it should differentiate into? So you do this by genetically modifying the cells so that when you add a small molecule to the media, they upregulate something called a transcription factor that directs the cell to become a specific cell type. And if you do this with multiple cell types, then you're able to pool the cells together to form a cluster of cells that when you instruct them with that small molecule doxycycline, they will co-differentiate into multiple cell types, even though they're sat in the same media condition. And in this manner, we believe that we would be able to specifically instruct every cell what to become, but get multiple cell types simultaneously differentiating, essentially overcoming that trade-off between complexity and reproducibility. What does this look like? If we take wild-type normal iPSCs, these are patient-specific stem cells, and we put them in a special media that instructs them to become neural stem cells, then in the absence and presence of that small molecule, you see they form the same cell type. These are called little neural rosettes. They look like little flowers, and they're very pretty, and it's an incredibly efficient protocol. You get near 100% formation of neural stem cells. This is what you'd expect. They're normal wild-type cells. They're only going to listen to the cues in the media that is instructing the cell what to become. If, however, we use an inducible endothelial cell that's designed to upregulate a gene called ETV2, that when we express that gene, it becomes an endothelial cell, we wanted to ask, what happens if we culture that cell not in endothelial cell specifying media, but in media that's telling it to become a neural stem cell? So it's receiving cues from the outside of the cell, telling it to become a neural stem cell. But inside the cell, with this upregulation of ETV2, this gene, it's becoming an endothelial cell. And we wanted to ask which one wins. And to our delight, we actually found that when you add doxycycline, you get near 100% differentiation into endothelial cells, even though these cells were cultured in a condition that would instruct them to become neural stem cells. You can see that in the absence of dox, we have near complete neural stem cell formation. Now this is really cool because now we can independently dictate which cell is going to become a neural stem cell and which cell is going to become an endothelial cell, even though they're grown in a single condition inside a well. And the same is the case for generating neurons. directly without going through neural stem cells. Again, absence of DOX neural stem cell. With DOX, we get this very efficient differentiation to neurons. And if we could do this, what if we could start feeding these different populations of stem cells into a printer and print out a stem cell tissue that's all just pluripotent stem cells, but underlying that tissue structure, when we add doxycycline, you can think of it as developing a photograph. We add doxycycline, and the different patterns of cells that upregulate different transcription factors might give rise to patterned tissue. So taking a look at what this looks like under a microscope, yeah, I don't know if the video is going to work, I'm afraid. Okay. So what you would have seen in that video is that the wild-type cells form spheres of neurons, and the red cells that were ETV2 become vascular networks in 3D. And if we start combining those into these pooled tissues, then we're able to actually create a cortical organoid that normally would have no vasculature inside because I'm telling it to become cortex, not blood vessels. I can dope in a small percentage of these special cells that upregulate ETV2, use the same protocol as published for generating cortical organoids, but now introduce a vascular network that pervades and surrounds that tissue. And after 45 days, you start getting these really nice developing cortical regions with underlying vasculature present. And then asking what happens if we bioprint these cells. Well, we can compact all of those stem cells into a slurry and actually print arbitrary patterns with pretty high resolution on the order of 100 microns in resolution. We can get good viability from the printing. The cells survive the printing process. And if we culture those cells for 4 to 6 days, the wild-type cells that are just receiving their cues from the media compact into this neural epithelial tissue, while the inducible endothelial cells and the inducible neurons form these vascular networks and sprouting sort of neural tissues, respectively. So what happens if we start to combine these 3 flows of stem cells together? Well, just like Aquafresh squeezing out of your toothpaste, you can kind of combine 3 flows and co-extrude them from a nozzle, creating a single filament, but with 3 different cell types. And when we did this on day 0, you can see the patterned 3 cell types stained in red, blue, and green. But if I stain them for pluripotent stem cell markers like OCT4, they would just look like a blank sheet. You can't tell, they're all pluripotent stem cells. But by adding doxycycline, by day 6, we actually develop the underlying pattern that we expressed with those genes. So we've now got a way of building a building block that's on the order of a millimeter in size. Think of it like a piece of couscous of tissue. But you're not going to get human-level function of tissue at that scale. You need to work at a larger scale. So I want to show next some work we do to combine hundreds of thousands of these little aggregates into a larger tissue whole. And our goal is to manufacture organs with hundreds of billions of cells, hundreds of millions of cells per milliliter. By volume, almost all of those tissues is made up of cells, not scaffolds. And that organization exists over the scale of centimeters down to submicron. And most importantly, when you have cells at this scale, with this many cell density, you need to have a pervasive vascular network to keep it viable. Yes?
I was just wondering if the genetic modification during the development process later on becomes a problem in the biological environment.
Yeah, so you can remove the doxycycline to remove the expression of that gene. So you can turn it on and turn it off. Only sensitive to doxycycline, and if you want to be really safe, you can flank it with lock sites or put it in a deletable transposon that you can pull back out again of the cell. So these 3 long-standing challenges in tissue engineering are being solved by the ability to make pluripotent stem cells, differentiate them into different cell types. The organoids that I showed before are able to deal with complexity at many scales by virtue of self-assembly. And finally, arguably the most difficult challenge is how do you keep that mass of cells alive? Well, there is this process called embedded 3D printing, where you can print, instead of layer by layer, you can deposit one material inside another. Now, that surrounding hair gel that this is being printed into needs very special properties to do that. It needs to be solid-like enough that when I deposit this yellow silicone into it, it holds it, that the yellow neither sinks nor floats. It needs to be liquid-like enough so that as the printer is dragging through that material, it doesn't just carve canyons and break up the material. It needs to be able to self-heal in the wake of that nozzle. Now, that is achieved in the case of hair gel because it is a viscoelastic, yield-stress, self-healing material. And we wanted to ask, can we get the same property, but just by taking a lot of cells and making them at a very high cell density? So working with Sebastian Uzel, we grew these little embryoid bodies. These are pluripotent aggregates of cells, stem cells. And we grew hundreds of thousands of them with lots of help from diligent undergraduates. We were able to compact them in a centrifuge into what is essentially a stem cell mayonnaise inside a syringe. So a biologist might think of it as a cell pellet, but actually if you look at the material property of a cell pellet, it has a viscoelastic and shear thinning and yield stress property. So we loaded billions of cells onto these rheometers, and we were able to sandwich it and measure the material response. And you can see as we increase the shear rate, it becomes less viscous. It's shear thinning. That helps it flow when we squeeze it. And we also found that at low shear stress, the solid-like represents how solid-like the material is, and the hollow represents how liquid-like it is. You can see it's relatively solid until we reach about 10 pascals of force, and then it yields. It gives way and flows like spreading mayonnaise with a knife. So this is ideal. We now get the really high cell density that you need to make solid organs, but we can also use it now for printing. As an ink, we actually get the kind of properties you want to 3D print either into or around those materials. See if the video will play. So this here is us loading about 1 billion cells into a slurry. It almost looks like a human Slurpee. And you come in with a printer nozzle, and we can lay down gelatin into that material. And those cells are able to be moved aside, and that gelatin neither sinks nor floats. It stays put where we place it. And when we raise the temperature of this tissue, all of those cells, those yellow cells, bind together. We have a little bit of collagen in there that makes it go from that Slurpee material to a solid. And simultaneously, the red material we printed melts. It's gelatin. And we're able to flush that gelatin out, and now we have channels that we can use to perfuse oxygen and nutrients through that very dense cellular tissue. So we connect a little pump up here in blue, and you can see the blue passing up through the corkscrew that we printed. And this was just for one tissue with one vessel, but if we want to make branching vessels that can pervade a volume with a single inlet and outlet, we're able to connect multiple lines of gelatin up printed inside of these very dense slurries of cells and actually maintain those cells in a viable state. So if I took those cells and they had just a thin shell of, if I took those cells at that high density, put them in a bath of media, and didn't have any vessels inside of it, then the outside survives, but the core ends up dying due to a lack of oxygen. But in that tissue I just showed being printed, because we're able to connect it to a pump, we're able to keep the core of that tissue now viable, green cells that got enough oxygen to survive. And so instead of just the outer shell represented by this dashed line surviving, we now get the full thickness of tissue that stays viable. Now, everything I've shown thus far is for embryoid bodies. These are pluripotent cells. It's not particularly useful if you want to make an organ, right? I mean, we don't have a pluripotent organ in our body. So we wanted to ask, can this work with anything that we can make little aggregates of tissue out of, or these organoids? And we did it using cerebral organoids and cardiac spheroids, really any sort of compaction of multiple of these little pieces of tissue has this really special granular property that allows us to 3D print vessels into them. So we wanted to scale up and really test this at large scale. So we took these little cardiac aggregates here, and you can see them beating just each individually like this. They're about 1 millimeter in size. Just going to make this bigger, sorry. Each of these are about 1 millimeter in size. Let's run that again. And you can see that they beat independently. Now, if we compacted these together and tried to make a larger tissue, that's not particularly helpful. If they're beating independently and they're not talking to each other, how are we going to have a heart that beats synchronously? So we wanted to ask, what happens if we compact them at high density and wait? Do they start to fuse together? And on day 1, you can see very little motion. There's a little bit of twitching here and there, but they're not really communicating very well together. By day 10, you can see that it's much more visibly fused. And those aggregates now beat as a whole, which allows us to really work at larger scale with these tissues and have them synchronize. So let's put everything together. We cultured about 500 million induced pluripotent stem cell-derived cardiomyocytes in the form of those little aggregates. And we were able to print a vascular network into it, remove the gelatin, flush nutrients through the inner channels, and then after 16 days of perfusion, we had this tissue that's 1 centimeter tall, 4 millimeters thick, beating and pulling on a spring. So really, this is kind of the first step, that we're able to now keep cardiac tissue viable at that scale. We can test drugs with it by flowing it through the inner vessels. But the next question is, how do we work, not even at the centimeter scale? What do we think about when we want to make full-scale heart tissue? And so the last story I want to just briefly touch on today is what happens if we use sort of these industrial-scale bioreactors to manufacture billions of cells. Can we start to get to the point where we can begin printing things at the scale of that initial pump I showed you? And it's really motivated by just how many cells are in every organ and our desire to get to a high throughput level of testing so that we can actually start to understand how do we optimize all of these perfectly reasonable questions. Any one of these I get asked, and they're great questions of, what are we going to do with the extracellular matrix? How do we get more maturity out of the cells? How do we make sure they conduct electricity fast enough that you get a nice synchronous beat at large scale? All excellent questions, none of which we can answer until we have enough tissue to really practice this regularly at scale. And if I were to get an undergraduate to do all of this culture, it would work out at about 200 flasks per biopump to be able to run. So it's really not a viable solution. And so we work in collaboration with Sartorius, they're a biopharmaceutical manufacturing company, to be able to optimize these industrial scale reactors, not for culturing monoclonal antibodies or with CHO cells, but instead working with iPSCs. And we developed this pipeline that allowed us to culture these cells in these automated reactors that can maintain pH, dissolved oxygen, temperature. They have many different reactors that we can run in parallel to optimize our culture. And by doing this, we were able to grow consistent large quantities of stem cells. So here you can see the aggregates growing en masse, and they had a good diameter for printing on the order of 1 to 200 microns in diameter. We were able to achieve cell densities on the order of 2 million per mil. So if that becomes a liter, that's 2 billion cells. So 2 liters would be sufficient for one of those large biopumps. And crucially, as the cells grew up in this reactor, we were able to take 1/10 of them and reseed a new reactor, and they would grow up again. So passage 1, passage 2, passage 3. We were able to keep these reactors running, generating billions of cells per week. So then we wanted to scale up from the 250 milliliters into these machines that can run up to 10-liter scale reactors. Shown here is a 2-liter reactor with 1 liter of liquid culture. And this is kind of the industrial end of our lab, generating all that raw material that we want to feed into our very hungry bioprinters. And you can see at this larger scale, in the 1-liter scale, we get really nice stem cell organoids that are 95% pluripotent. So with these very high quality cells, in the larger scale, we actually got even more cells per milliliter, approaching 5 million per milliliter on some of our cell lines. That's 5 billion cells in a single aggregate. And if you recall, that 5 billion number is the number of cells we're going to need to start making these pumps. So I want to just finish on here to show where we're moving. So we can grow the stem cells, but can we make the cardiomyocytes? And so Stacy Lee in our lab has shown that at this 1 liter scale, we're able to manufacture really good quality troponin-positive stem cell-derived cardiomyocytes on the order of 85% pure for the cardiomyocytes. And when we take those and spin them down, we get an almost 20 milliliter pellet of induced pluripotent stem cell-derived cardiomyocytes. And that is the scale that we're going to be needing to work on these pumps. So I think with that, I'd like to acknowledge the collaborators. Jennifer Lewis' lab was where I did all the work in bioprinting of vascular into tissue. I'd like to thank Sebastian Uzel, my co-first author on that. Jeremy Huang and Eric Liu were my co-authors on the transcription factor work. And Stacy Lee and Debbie Ho for the work we're doing on the large-scale bioreactor derivation. With that, I'm happy to take any questions. Yeah.
I have questions about mechanical side. You showed basically two methods. One for flat surface, right? Then you have mixing nozzle. Another is in gel. And question of size, right? For one, you showed opening of 250 microns, I believe.
Yep.
And in gel, you didn't specify, but assume it's big. Is repetitivity and leaking nozzles important for you or not? And what is your target size? How small do you want to go?
Yeah, so in an ideal world, we'd love to print every single vessel in the organ, right down to the capillary, 5 to 10 microns in diameter. But if you do the maths and figure out the length of the capillaries that are in our body and put them end to end, it goes to the moon and back. So we don't intend to run a space program. And so we're going to rely on the self-assembly to make things at the smallest scale and have those connect to the larger vessels. So on the order of 1 to 200 microns, which is around the diameter of an arteriole, is probably the right approach for the printer. And then the key is to have those little microvascular networks that you saw in the ETV2 overexpressing cells connect up to those bigger vessels. We thought it would be quite straightforward. It's actually harder than we think. It's not a robust process, getting those two scales to talk to each other. So we have a few ideas in lab on how we want to try and improve that, and we'll be excited when we get the tissue to really start testing some of our hypotheses. In terms of reproducibility, it's pretty good. I mean, motion control is a pretty solved problem. You can get 20 nanometer precision on a bioprinter. You can get very precise manufactured metal capillary tubes that have the exact diameters you need. Machining is very good. So I don't worry so much about the reproducibility from the printing standpoint as much as I do as just the true scale of producing things from 5 microns up to tens of centimeters in scale is daunting. Yep.
Yeah, just to be mindful of the schedule, we'll take more questions at the lunch if you're around.
Yep.
But yeah, so now we're going to move to our last session before lunch. So I'll do a quick introduction of the speaker for this session and the session in general, and then we'll have lunch, and there'll be signage and people outside helping everyone get there. So give us 1 minute to set up, and then I'll introduce our speaker.
Oh, thank you.
Okay, so quick introduction of our speaker for this session. This is Professor Jin-Hung Lee. She's an associate professor of neurology and of neurosurgery and bioengineering, and by courtesy of electrical engineering. She received her master's and PhD in electrical engineering from Stanford University, and her lab uses interdisciplinary approaches from biology and engineering to analyze, debug, and manipulate system-level brain circuits. all in the aim to understand the connectivity and function of large-scale networks in order to drive the development of new therapies for neurological diseases. So take it away.
Well, thank you very much for the introduction. It's a great pleasure to be here on a Saturday with all these enthusiastic students who are interested in making a change. And so my lab in general, we work on, one way to summarize it is that we work on creating a digital twin of the brain. And our lab also, a lot of the work that we have done has now reached a point where it could make some impact on how we design diagnostics and therapeutics. And so that effort has also been supported by the Stanford Biodesign program and also StartX to create this company called Elvis. And so I'll tell you a little bit about that as well. And so I recently on my flight somewhere, I can't remember where it was, but I was watching Harry Potter again. And I don't know if you all remember, but in Harry Potter, in some scene, Harry asked Professor Dumbledore, like, I was initially assigned to Slytherin, and then I said I wanted to be Gryffindor, so that's why I was assigned Gryffindor. What if I am really a Slytherin? I remember like watching that where Professor Dumbledore says, it is not our abilities that show what we truly are, but it is our choices, and that has been a very important that's a message, when I first watched it a long time ago, I don't think I fully appreciated it, but that's something that has been a very important message that when I saw the movie again, I was like, yeah, that's so right. And there was such a profound message in that movie. And speaking of choices, one of the things that has guided my choices in general has also a lot to do with my problem-solving approach. And Euclid said there's no royal road to learning. I think that's even more true for problem solving. And so in general, for problem solving, one of the things that people also all talk about a lot is going for the lower hanging fruits, but I kind of tend to disagree. I think it's really important that we approach problems in a way that, if you want to take fruits, create a fruit picking robot that picks fruits from every height instead of going for the lower hanging fruit. And with that principle in mind, in general, I've been making choices that is more like taking the path of strongest resistance rather than taking the lower hanging fruit approach. And as I've been introduced, I have been educated fully all the way to my PhD at Stanford as an electrical engineer, but now I work in neuroscience where I decided to tackle the problem head on. What happened was actually around the time I was finishing my PhD, my grandmother had a stroke. And it was a really difficult thing to watch her suffer through 12 years of bedbound life. And that's when I realized, oh my God, they don't really have any solution to brain disorders. And as an electrical engineer, that was a very puzzling thing. Brains are circuits, they tell me, and there's interconnection, it's a function that drives all our behavior. How come the solution to that when there is a disorder is to basically just watch and see and do rehabilitation? And so that is when I realized, maybe approaches in engineering, electrical engineering in particular, could be used to solve this brain health problem. And I did a little bit of research. I looked around, do they really have a way to understand brain circuit functions the way we do in systems engineering approach in electrical engineering? And the answer was no, so I decided to take on the challenge myself. It wasn't very easy, being an Asian woman from another country, outsider, utilizing different approaches. Academia, we all talk about wanting to drive innovation, but in reality, it's actually a very conservative organization that likes to make innovations in very specific directions and steps. And so to continue my approach, it was a very challenging step. And I think in general, I had to put about twice the effort or more to get to a result or to try a vision that I wanted to try. It wasn't quite like that when I was just an electrical engineering student doing electrical engineering, but it was actually very challenging. But while it was challenging, one of the reasons why I could still continue to pursue all of my ideas was because of the generous funding that a lot of people provided. And whenever I think about all of this, I think about all the people who were in the room doing the reviews of these grants. And yes, because it was not a conventional idea, like I had to write 3 or 4 grants for every grant that I was getting funded, but somebody gave me the chance, and we were able to pursue these ideas. And so with all of those generous support, actually the NIH K99 grant was what allowed me to first get into this neuroscience from electrical engineering. And now, after all those years, my lab is in the BioX on the 3rd floor, on the upper right there. And yesterday, we actually had a symposium, Neuroscience Preclinical Imaging Lab Symposium. This is a resource that I brought to campus after 10 years. It took exactly 10 years to bring this research onto campus. And now we have this preclinical imaging system that is available as a resource to all of campus. And to promote science around this, we are now having yearly symposiums, and yesterday was the 2nd symposium that we had. And so we give pilot grants, and through those pilot grants, we are also facilitating neuroscientists who are typically not using imaging resources that look at whole brain scale imaging with things like magnetic resonance imaging. We are sponsoring them. We're also bringing outside speakers and doing education for people who are not experienced in it in order to facilitate innovation in this direction. And with that in mind, the main problem that I decided to tackle was brain health care. And brain health care is actually a very significant growing concern every single day. There are neurodegenerative diseases, which is mostly related to aging, like Alzheimer's disease. It's not only a huge problem right now, but it is increasing every day, quite dramatically. And it's also true for developmental disorders like autism, where children have it. And this, in 1970, was 1 in 10,000. Now it's like 1 in 36. And so it is quite a dramatic increase. And also things like COVID and social isolation also driving various brain disorders. And so brain disorders is the #1 cause of disability worldwide. There are 1 billion patients worldwide, and just this country alone spends $1 trillion a year in cost. And this is not to cure, this is to simply maintain the patients in different states. And so while this is a really big problem, it's increasing. Because of that, of course, not just on academic scale or different private companies, many governments recognize the importance of addressing brain disorders, and there have been significant investment made to date, and that is making very big advances in various places, but there is no clear solution to date. There is nothing that is changing the curve of this big upsweep. And in trying to solve this problem, one of the things that was most notable to me was that when you're trying to solve a problem, what's most important? Any thoughts on that? What's most important for problem solving? You have to know what you're solving. Problem definition is the most important. The problem is, in brain disorders, they are unable to define the problem. The current state-of-the-art diagnosis of brain disorders is an example of one of the tests in Alzheimer's. It's a questionnaire. It's like you're trying to fix your phone and you go to the Apple store or wherever, and they just ask you, what happened to your phone? Did you drop it in the water? All those are very important clues, but imagine fixing the phone with just that knowledge. It's impossible. And so when you can't define the problem, one of the things you do is you stick to something that you know. And one of the things that they know in Alzheimer's disease, for example, just like asking about whether it was ever dipped in water, there are protein, like aggregated proteins, these plaques. And so that has been one of the things that people have been really focused on trying to get rid of, every effort costing more than $1 billion. And that has pretty much all failed. There were 2 drugs that were recently approved last year and the year before, but there are a lot of questions about whether this does much of anything, but it did meet some clinical endpoints, but there's also a very large set of side effects. And so because of numerous failures in drug development, where the problem is somewhat ill-defined, some of the things that has been tried out in the recent years is what's called digital therapy. And initially I was really confused what digital therapy means, but it means everything that's not drugs. And it relates to a lot of different biological signal measurements and generally trying to use that to cure brain disorders. And it is, I must say, there are some things that can be addressed with that approach, but that's something that's not going to lead to curing Alzheimer's or Parkinson's or any other disease for that matter.
And so while that is happening, another interesting angle is what is called electroceuticals. And these are approaches where you put electrodes inside the brain and you give electrical pulses to try and restore brain function, which is actually somewhat of an obvious approach because it's an electrical system. You put electrical signal to correct for the erroneous signal that is happening in your brain, which is great. But one of the biggest problems with this approach is that you are also doing this blindly. You don't know how the brain works, so how are you going to put signal in there to fix the problem? And so, of course, it's not completely blind. You do this based on some knowledge of these areas of the brain are somewhat involved in the disease related to what we're trying to fix. And I tried putting it in animals and nothing bad happened and it seems to correct some problems. And so let's try it in humans. These trials take $500 million. And after that, it's there's a little bit of improvement, but maybe not for others. It's a very complicated process that's happening. And also, when you do something without knowing what you're doing exactly, what happens is when it doesn't work, you don't know why it doesn't work. Also, diseases are progressive. And even if it works certain times, when the disease progresses, it's I'm not sure why it stopped working. And that is a very significant problem in trying to address brain disorders. And so in trying to solve this problem in a fundamental way, one very obvious question that comes to the surface is that brain health care, brain disorder treatment's ultimate goal, no matter what, is to restore brain function. Do you agree? Your goal, when you do the clinical trial at the end of 12 years, what you do is you do surveys, see if their memories increase. That is actually testing for whether it actually restored brain function. That is the goal. That's the problem definition. So I would argue the main reason why we have failed to date with all the brain disorder treatment is because you failed to quantify your goal. And so when you're doing something as simple as maintaining your weight, imagine doing that without measuring it. Okay, you can look yourself in the mirror and go, I look a little more chubby around my stomach. Okay, maybe my weight increased. That's probably true. But even for a single parameter value that you're trying to optimize, if you don't measure it, it's very difficult to maintain the weight. And so you do need a measure of the brain function in a very meaningful way. And when I say that, sometimes people say, oh, no, there's a very pretty picture that you can take with MRI of the brain, but these are not measure of function. These are showing different anatomical structures, including blood vessels here. But there is no good way to measure how the brain is functioning. And so it is critical to directly measure how the brain circuit elements communicate. So if you want to intervene the system, you have to know which elements are talking to which to create the behavior that we're all seeing in our behavior. And in creating that, what you need a measurement of what the brain is doing. So if you have a good model, what it should do is be able to explain, be consistent with the measurement you already have. You also have to be able to explain why those measurements occurred, what exactly occurred in order for the measurements that you observed as occurring. Another very important feature of a digital twin that is useful is you need to be able to predict the future in terms of what you haven't really measured yet. And so if you have sufficient consistency with the data that you have created a model that can replicate what goes inside, then you should be able to predict, for example, optimal therapeutic intervention without actually doing the experiments. And so we've been at this particular problem for a little, it says 15 plus, but a little less than 15 years. And starting with brain circuit analysis technology development, we applied this to various brain disorders, and we are now able to create a digital twin that does what I just described. And so in terms of actually defining the problem, one of the things that we did was, yes, when we say we want to create the digital twin, one of the things we want to be able to do is to make the problem simpler than just saying, I just want to know how the brain works. If you have a specific behavioral unit, you need to be able to describe what happened inside the brain to create that unit outcome. And so in this case, we are manipulating the brain function with optogenetics, specific genes targeted, and manipulating it in a particular context of disorder. And for that particular behavioral unit, we are now able to create communication diagrams of who talked to whom in order to create that behavior. And so this consisted of developing imaging techniques with MRI, genetic control, and then we can now measure global brain function driven by different cell types. And here, these are images just showing 2 different cell types driving different function across the brain. And on the lower left, you're seeing the time series that we can reconstruct from each one of the brain regions. And we can also do things like single unit recordings to check for things at single brain regions. And so with that, what we're able to now do is to create these communication diagrams. This is not a connectivity diagram. Hardwiring is different from function. The fact that we all have phones doesn't mean we all call each other. You have to know who's calling whom, what communication is occurring during that behavior. And so this is a communication diagram of 2 specific cell types that are very important for Parkinson's disease in particular. And by having this large-scale communication diagram, what we were able to do then was to get a more refined scale of information, which is single unit spikes. How do they communicate? These digital spiking, how do they communicate in order to give rise to this larger context of function that we see? When you don't have the broader context, it's very difficult to reconstruct what's happening within the circuitry. But once we had a more global picture, in a 2-step approach, just like Mark was saying, you can actually start to reconstruct this. And so now we are able to create models where you can simulate single unit spikes. And so on the top is what's in a context of, let's say, D1 medium spiny neuron stimulation. And on the top is the measurement. On the second row is our simulation. We can do this for different stimulation contexts, and they all show similar spike rates, for example. And with this model, we have now tested whether we can predict the future, as in if you do different DBS stimulation, for example, which one gives the proper prediction of how it will best mitigate for example, beta oscillations in Parkinson's disease. And we just randomly pulled out a paper where they did a lot of experiments in animals. And what we could do was, by doing these simulations, I'm sure those experiments take many, many years to do. By doing these simulations, we could find in minutes what is optimal, and they were consistent with experiment results that were not even produced by us. And so that was one significant path we took. Another direction that we wanted to investigate is one of the key features that drug companies focused on. There are aggregated proteins in the brain, which is somewhat of a hardware defect in the brain. And how do those hardware defects relate to function is something that we wanted to know in order to see, okay, our goal is to restore brain function, but when you restore brain function, what happens to the hardware defects that people have been focusing on? And so while there is no knowledge about these aggregated proteins forming, one of the things that people found is that they tend to spread. And so we first wanted to quantify how these spreading occurs. So we went through 2 years of data to kind of figure out how they quantitatively map. We used 3D brain clearing techniques to image them, use machine learning to segment them, and then later on build computational models to show how the spreading pattern works. We first were defining the baseline so that we can then see relationships to other things. And one of the things that we could do now that we have that model was to also see if different genes contribute to spreading or degeneration as part of this whole process, and we could quantify them now. And another thing that we wanted to test when we have this knowledge, once we had this knowledge, was to see what the function does to it. Once you have baseline, you have the capability to quantify it. And for example, on the left here is the image that we get from neuromodulation and imaging the functional consequences of it. And you can see that there are some increase and decrease in function region that you can directly see with these imaging techniques. And on the right, this is a map of what happens with the same neuromodulation to these plaques. And do you notice some similarity? Actually, I think the quantification is not included here, but did something? Oh. But what happens is for regions where there is functional decrease, there's increase in plaque, you see with green, and where there is functional activity increase, you see that there is decrease in plaque, as seen in red, which shows, for one, that neuromodulation, changes in brain function, can change plaques. The hardware defects are changed as a result of functional change. And another thing that we can tell is actually it's not only changing, it is very directly related to which areas have increased and decreased activity. So from the disease point, from the aspect of trying to think of the origin of the disease, there can be many reasons why the disease came about. But one of the things that you can imagine is once you have defects in the brain in terms of hardware, it could have software problems, but once you have software problems, there's hardware problems. And so it is likely an iterative process that leads to all of these degeneration happening. But what is now clear is that functional restoration not only achieves the goal of functional restoration, but it also has impact on the underlying hardware function. And so with all of these different developments, we also wanted to deliver this to the clinic. And so we founded this company called ELVIS. It stands for Live Visualization of Brain Circuits, which was supported by Biodesign and Stardex. And what we can now think about going into the future of brain disorder treatment is, what would the future of brain healthcare look like with the digital twin where you can replicate the function and predict what it does? And in doing so, what we thought was we can do AI-driven data analytics to first collect brain data and find important events associated with what we want to look at, as in defining the behavioral interest unit as was defined in the early stage of research. And then what we can do is to do brain network analysis to create these digital twins. And based on that, you can do design individualized treatment plans and also develop new therapeutics that are targeted towards restoring brain function. And this ultimately will lead to improved outcomes and also decreased costs, which is a very important factor in brain disorder treatment. And so by having an approach where you can define the problem very concretely, instead of discovering, we can now start to design brain healthcare products where we can imagine a situation where a simple digital twin based health checks can be conducted. You can also do detailed digital twin based analysis of brain disorder, which can be which can replace all the different kind of survey based diagnosis. And once you have the goal very clearly defined, right now, for example, even for the limited options you have in clinics, what doctors would do is, give you let's first try this. If this fails, okay, why don't you try that? And some of these options are actually cutting out your brain or putting a very invasive neurostimulator in your brain. And the doctor's question will be, what would be your question if you're the patient and I'm recommending that you cut out your brain? What's your first question? Huh?
Safety, is that really good?
Safety would be one thing, but aren't you curious about something else before you ask for safety?
I lose functions.
That's important too, but before any of that, I would ask, what?
Is there any other option?
Yeah, I usually give you that option because there's no other option, but what would you ask when I say look, I think right now we ran out of all other options, let's cut out your brain?
Will I be alive?
You guys are very nice people. I would first ask, would it work? And I mean, whether it's safe, whether I'll be alive, all of that doesn't matter if it doesn't work, right? I don't want to do it if it doesn't work. The question, the answer that the doctors can give now is, I don't know. But this is your only option, but just try it. But we don't have to do that anymore. When you have clear understanding of the problem that you're solving, then you can select treatments that actually literally match to the condition that you have, and this also allows personalized treatment development. And so we can take this whole discovery-based field from discovery to a design, more engineering-based solution. And I talked about making fruit-picking machines instead of going for lower-hanging fruits. One of the things that we discovered along the way as we're making a discovery of how the brain computes is that brain actually computes in a very different way from our von Neumann architectures. And so one of the things, even though we're really excited about ChatGPT and whatnot, what the AI can do, one thing that's also being ignored is the fact that even what they can do right now with AI, they're doing it with enormous energy. Everything we do right now, like that we can probably do a lot better than AI, we do with very little energy. We eat 3 times a day, perhaps that's kind of it for your energy source. But all the things that these chat GPTs and whatnot are doing are using enormous energy, both for data storage and computation. And so if we really want to take AI to a level where we can utilize it in the way that we imagine, we need to actually have a solution that consumes much less energy. Because at this current rate, by 2040-ish, we will just run out of all the energy that we produce just for using it for data storage, for example. And so one of the things that we are learning is that we use computers, we use the AI tools that we have to actually cure brain disorders, but in the process, one of the things that we defined is how the brain computes. And the brain computational principles are now informing us how we might be able to design different computing models that might enable general AI in the future. And that is just for saying that taking the strongest path of resistance and actually making that machine tends to have extra benefits. And one of the things I wanted to mention at the end of this talk is that, you know, in the fast-changing digital world, strong value system is a key to making decisions. And earlier they were asking about different advice. This is the most important advice that I wanted to give you, which is that, you know, having a value system, there are many, many things one can do in life, but you have to choose. You're always choosing what to do. And in choosing, having a strong value system is very important. And 4 most important values that I tell myself and also to the people I work with is that to strive for excellence, have integrity, have positive attitude towards anything that you're doing, and also to grow every day compared to what you were doing the day before. And to expand on some of the thoughts around overcoming all the difficulties I have to date and like guiding principle of how I intend to do things going forward is that you have to pick problems where it will help people. I mean, there are many ways to make money, for example, but you don't want to do everything that will make money necessarily. And, you know, in doing things, you cannot do anything alone, so being grateful to those who help you is very important. Another thing is having courage to and being ready to take on new challenges at any time. There are opportunities that knock at your door every day, but if you're closed-minded and you're like, oh, I'm already pretty good at this, like, I don't want to do that, it actually tends to take away opportunities from you. And criticism and obstacles, as much as we hate them, it is important to listen to them. It is not good to listen to criticism and go like, oh my God, I can't do it. It's not meant to discourage you, but not listening to criticism also tends to lead to lack of development in general. And so that, I think, is very important. Also, being humble and not thinking anything is beneath you in any circumstance is really important. Once you're already a Stanford student, so you're very successful people, but having this thought that I'm a Stanford student, that's beneath me, I can't do that, that's actually a great impediment to your development. And so I would think that is very important. And focusing on the long game in general is something that I have always took to heart in making decisions. And keeping your mind and heart open, like as you go through a lot of different obstacles in life, you're gonna be like, oh my God, like that thing happened to me, that happened to me, and it could actually harden your mind as things happen. But we are all here to make our society better. And to do that, having this kind-heartedness, love for your neighbors, very important. And so in general, I just introduced you to some of the choices I've made to date. I found a problem that I'm passionate about, good at solving, and that has great societal need to solve. And in making all the detailed decisions along the way, I relied on the value system that I shared with you. And while there are some successes, there's going to be more challenges to come. So success is not final, failure is not fatal. It's the courage to continue that counts. From Winston Churchill. That's one of the main guiding principles of what I do, how I see the work that I do. And we're generally building a community to achieve a common dream of curing everyone everywhere. So that's how I would. Thank you for your attention. Any questions? Yeah?
Can your work on the brain, the digital twins on the brain, inform not just like personalized treatment, but actually drugs?
Absolutely. So one of the main points I want to make is that the drugs were designed based on wrong goals, right? I mean, removing plaques, for example, okay, plaques are there during disease. Maybe it's better to not have the plaques than have it. But this is what we're facing, for example. For 10 years, you do clinical trials on endpoints to remove the plaques. And then at the end, you test by doing surveys. Is your memory better? No. So then that's a failure. And so one of the things that is important in design and evaluation stage both is to do it on proper goal. And so for drug development, for example, if I know that my brain communication for this patient is weakened from here to here, it should be a 10 and it's now a 5, what you can do is to figure out, okay, you go into details of the circuitry. What contributes to the communication between this node and that node? And if you can find a way to enhance that, that is your solution. And so it's not just drug development, whether it's neuromodulation, whatever solution that you use to restore brain function, it has to start on a proper goal. Yeah.
So you mentioned a lot about like now based on question you can ask to assess how the brain works and what's the solution? Is the solution maybe based on MRI image of the brain?
Yes, no, not really. Currently, one of the biggest thing is when you go to the clinic, when you have when you are suspecting maybe I have Alzheimer's, what they do is they ask you questionnaires as a way to evaluate function. They also take an MRI of your brain to see if you have a tumor, but mainly to assess the function, it's done through questionnaires. And what our solution approach to this is, I need to assess your function directly. I need to measure your brain function and be able to create a digital twin, so to speak, so that I can tell, okay, communication from here to here is off. And so to collect that information, we use various different information. And the clinical setting application is one, what we do for the lab is another, but generally we use techniques that can measure brain function. So, like for example, when we're building the model, functional MRI was one of the very important tools. Yeah. You had a question?
Yes. So, first of all, thank you so much for the talk. So, a lot of your talk focused on improving like quantification of how we use this function, for example, providing high quality data. So, as like there's this sort of movement or transition towards at-home health, how are you thinking about this space specifically with regards to like brain health and brain function? Like, where is the role of like remote patient monitoring, at-home health in this whole process, and how does the clinic change in response to this?
That's a really, really good question. And what we're trying to do is starting by solving the more complex problem of getting a detailed model of the brain that could be used in the clinic so that the doctors can assess things. Once you have a detailed picture, let's say like you have a high resolution image, making a low resolution image out of that is very easy. It's very difficult to go the other way around. So we're solving the problem of getting the high resolution image, but the way we might approach the in-home care is that you take the low resolution version of it and then monitor to see if there's any anomaly that's associated with what you might pick up at home and decide to go to the hospital. Yes?
How do you include the biological mechanisms, for example, neurotransmitters in the model?
That's a really good question. One of the things that we decided early on that was very important to understand it is to, at the very basic level, like different cell types that use different neurotransmitters, for example. But the model that we currently made is focused on the spiking activity. That's the level at which we model things. But once you know that big picture, first, we actually started with regional interaction. And that regional interaction map, once we had completed it, we could then understand the spiking level interaction. But now that we understand the spiking level interaction, we also are now starting to gain understanding of a more molecular interaction. And so in general, the approach that we're taking is multi-resolution approach, and that is the next step that we're incorporating. Yeah.
One of the paradigms and theories in neurodegenerative diseases is how that exactly is sometimes these amyloid or fibrils, for example, like or alpha-synuclein or these toxic proteins kind of like travel along connections.
They do travel along connections, yes.
So and this was some way that was showed also by Seeley in 2009 and some years ago.
Yeah.
So I was wondering from your work with these connectomes, does that validate the theory? Does it suggest something slightly different?
So that's a really good question. What we have done, as you've said, they've shown that they travel along axons, like things happen, but they didn't fully finish the quantification. So it was very hard to tell what it means exactly. Being an engineer, I can't deal with that. So what we did was actually create a whole pipeline where we can fully quantify it. So what we have found, for example, is that these traveling are more retrograde than anterograde, for example. And so yes, it follows along axonal tracks. That's not the end of the story. We found that it travels more along the retrograde tracks, but it also does some anterograde traveling. And also there is some diffusion element too. And so once you quantify it, you can actually put weights on them. And so we found out that yes, that is the case. And to put the puzzle together to the next level, what we did was this next experiment, for example, is, okay, they do have this traveling quantities. How do they relate to different gene expressions, for example? So that's where we looked at the gene expression quantifications and used it as parameters to see how they impact the data and model fit in order to evaluate things. And then the other thing that we wanted to know to relate it back to function. The earlier work that we did was to create a model of the function. And then to relate it back to function, we did experiments to see if, okay, I changed the brain function. The most easy way to change brain function is to just do neuromodulation, just inject signal. We inject signal, it changes these plaques. And so that's not the full story. We need to investigate further, but what we have established here that's very important is the relationship between function and the plaques. And so, does that make sense? Yes, yeah. That's my question. Just one more? Yeah?
Yeah, so it looks like if you focus primarily on the neural components, spiking and functional.
Yeah.
Without the significant non-neural components,
That's those are also really good questions. And so the reason why we focused on neurons is because neurons primarily are the direct output nodes of the function generation, right? And so we created models where we can describe the function. Then you can, just like other molecular contributors that could come into place, different cell types that are non-neuronal cell types and how they interact with the neurons can now also be integrated into the model to understand their contribution to function. Putting it in engineering terms, what I wanted to do was to first define the objective function. And so this objective function is the function that I can directly describe from neuronal measurements, but then there's a lot of variables, including non-neuronal cells. And so that is the approach that we are taking. We're not done with the whole thing, but that is generally the approach.
So that the neuronal state percentage, the state space,
Yeah.
is sufficient to describe it. So a lot of people look at Alzheimer's, for instance, as an inflammatory disease. So
inflammation, in my mind, is a variable that contributes to brain function changes, which is why you lose memory, right? And so I think one way to put it is people have been defining the objective function differently. They define it as plaque, normal plaque, 0, patient plaque, certain level, minus. That's, minimizing that was the objective function. Now, from the inflammatory angle, it's like 0, minimizing inflammation was also an objective function. But I think those are all wrong, is what I'm saying. I may be wrong, but that's my current thought, which is that the objective function should be brain function. It's obvious because even at the end of any drug, like if you were having Alzheimer's disease and you took the drug and inflammation went down, but your memory is the same, that by definition is a failed drug, right? And so what you are trying to achieve when treating brain disorders is to normalize brain function. It's very obvious. So your goal has to be to define brain function. In my opinion, the reason why people haven't done that is not necessarily because they don't understand that. It's because there is no quantification method for brain function. You simply can't measure it, so you decide to ignore it. That's sort of what happened. And so as a person who had to tackle the problem more like from the fruit cutting machine approach, we just decided to tackle it all the way to develop models of brain function.
Yeah,
yes.
I completely understand the viewpoint, but it's just,
Yeah.
there's some people
chemical encoding is what drives the electrical outcome. Electrical encoding is the more closer version of, so there are chemical encodings that contribute to electrical encodings, which creates your behavioral outcome. I think you're arguing maybe the electrical is less close to the behavior than chemical. Yeah, maybe, maybe not, but yeah. But what I would argue is that when I speak, when I run, the signal that has the highest temporal fidelity in defining my behavior is the electrical signal. That is why we decided to encode the electrical signal first. That is not to say that the chemical signal is not important. Does that make sense? It was a less closer to behavior variable. Yeah. Thank you.
All right, so now we're going to be moving to the networking lunch. So that'll be taking place outside in the courtyard, I believe. And yeah, so feel free to make your way over there. We have catered food, I think Chipotle burritos for everyone. And food and snacks and all that stuff are going to be out there. And then we will resume back here for the afternoon session at approximately 1:15.